Alrighty, cool. Well, let's get this presentation started. We're pretty excited. This is Group 4-7. We're going to talk a little bit about the how behind how the internet works. We've learned a lot about it this semester, and we wanted to delve a little bit more in depth of how the cables work and stuff, and how the ones and zeros actually get transmitted. So, welcome to our bits, bytes, beeps, and boops presentation. First, we're going to start off with a little bit of general history. How did we get to where we are today? So we've already talked a lot about in class some of the first days of the internet, but a little bit of context. Why was the internet even created? Some of you might remember this. Dr. Schetzler mentioned it a few times, but in the 1950s, we were in the Cold War with Russia, and we wanted to beat them. We were constantly under the fear of nuclear attack, and during the 1950s, we were focusing a lot on manufacturing for like cars and stuff like that, and we kind of let our space program drop a little bit, and that gave the Russians the opportunity to launch Sputnik into space, the very first satellite into orbit. And this gave the United States a big scare. We were afraid that we could potentially lose the Cold War. At that time, probably our main form of communication was through phones, and so the fear was our phones were kind of like a bus network where so everything is all connected to each other, but all through one main center of main line of communication. So if at any point along that line something breaks or goes down, everything's offline. So that's how the phones worked back then. And so the fear was if the Russians could place a missile in the correct spot, they would take down all of our long distance communication. And so the United States wanted to combat that. We wanted to protect ourselves. And so they founded ARPA. ARPA was the Advanced Research Projects Association, and their goal was to kind of combat this, and they formed ARPANET. ARPANET was very primitive when it was first started, but the basic idea behind it was we want to be able to send specific blocks of data or specific messages to specific locations through different paths, right? So we don't want just one line of communication. We don't want a bus system. And so it's actually kind of funny. The very first message they tried to send through this line was login, just 5 letters. Only the first 2 letters made it to the other computer. So it's kind of interesting, but that was the birth of ARPANET, and kind of when the internet we now know first really started to be developed. It was the first form of packet switching. And so we're going to talk a little bit about the innovations behind that and how did we get from just getting 2 out of 5 letters to a computer to where we are now. So we're going to have Brian talk a little bit about that. So, yeah.
So as you guys know, right now, the internet as it is not what it used to be. In the early 1970s, the Xerox Palo Alto Research Center in California invented what was known as the Xerox Alto. Basically, it was the first computer workstation with graphical user interfaces and mouse pointing devices. Now, in 1972, Bob Metcalfe, who was currently working at the Research Center, developed the first experimental Ethernet system to interconnect the Xerox Alto. And the experimental Ethernet was used to link Altos to one another, in addition to linking them to servers and laser printers. Now, this first experimental network was known as the Alto Aloha Network, kind of like what Hunter was mentioning, which was later changed by Metcalfe in 1973 to, as we now know, Ethernet, in an attempt to make it clear that the system could support any computer and that this network mechanism has evolved beyond just the Aloha system. Now, the name Ethernet was chosen in an attempt to describe the essential features of the system. The concept luminiferous ether was once thought to propagate electromagnetic waves through space, much as the same as the cables from the internet carry the bits to all the different kind of stations. Now, with the bringing up of this network, this Ethernet, came a few different standards. The original 10 megabit per second Ethernet standard eventually became known as the DICS Ethernet standard, which was contained the specifications for the operation of Ethernet, as well as the specs for a single media system based on a thick coaxial cable. Now, this standard was later revised to add some technical changes, corrections, and improvements. And this last kind of revision of the standard is known as the DICS V2. However, along with this upbringing of the internet, there's the electrical electrical and electronics engineers worked to develop a standard as well, which would develop the open network standard, more commonly known as the IEEE 802.3. Now, this IEEE 802.3 standard is now the official Internet Ethernet standard. It made several technical changes that were necessary for inclusion in the worldwide standardization effort. And while you may hear of other Ethernet technology standards developed by various groups of technology, it isn't specified within the IEEE 802.3, then that standard really isn't an official Ethernet technology. And as we've kind of developed this Ethernet, we've developed some recent innovations as well. And so we've got the single pair Ethernet, or the SPE, which basically is a form of Ethernet that uses a single twisted pair of wires, whereas other forms of Ethernet use 2 or 3. And so with this, what we have been able to do is actually make the maximum length of the cable up to 1,000 meters, which is 10 times that of which previous industrial Ethernet forms had before. In addition, we've created the advanced physical layer, the APL, which is it's a type of single pair Ethernet combined with 2 wires, intrinsically safe Ethernet capable of being deployed with pre-existing field bus type A cabling for use in a hazardous environments. Now, along with these recent innovations, though, have some downfalls. For instance, the SPE, or the single pair Ethernet, the communication speed is 10 megabits per second, while other forms of cable that we have used before have reached up to 100 megabits per second. And so, if Will, you want to go ahead and kind of explain a little bit of the how and kind of how this process works?
Yep. Thank you, Brian. Thank you for that overview, and Hunter, thank you for that history. That was super interesting. I'm really excited to talk to you all about how it actually works, the physical devices and the things that make it so a bunch of signals or light can actually travel through these wires and get to your computer. So on the next slide, we see a couple of the cables that we mentioned. Dr. Schetzler goes over these in great length, so I'm not going to get into them very much. On the next slide, we see our favorite OSI model. We know that we've learned about how everything comes down from the application layer, gets the different headers, and gets encapsulated all the way down to the physical layer, which that's what I really want to dive into today. So let's go one more slide. Now, in the end, what actually goes through the wire, what goes through the cable are bits. And as you can see from the diagram, to differentiate between a bit that's a 1 and a bit that's a 0, you either have an electrical charge. In this case, if we were using copper wires, you have an electrical charge, which is usually about 5 volts, and that's a 1. And then a 0 volt charge or no charge is a 0. And the computers that are establish the connection, they determine the amount of time it is going to take, so that they know how to distinguish between a 1 and a 0 in that particular connection. Now, when you're talking about a couple of bits, that's easy to understand. Yeah, you flip the switch on, you flip the switch off, do it a couple times, and you've got some letters flowing. But we deal with internet speeds like Brian was talking about that are so much more than just 1 or 2 bits. If you think about a 10 megabit download speed, right? 10 megabits per second. That means that every single second across that wire or through that fiber optic cable, 10,485,760 bits are being transferred. That's every second. And you know, that brings to mind what Dr. Schetzler always says when he's talking about the physical layer. This stuff is awesomely amazing. So what are some of the devices that actually allow that transmission to occur? If we can head over to the next slide. When you're talking about copper wires, like our example was before with the electric actual voltage, you have what's called a current driver. So that's what's going to do the flipping on and off of the electrical current, which is going to determine the bits that are sent across the wire and then received by the other computer. if you're using light, if you're using a fiber optic cable, you'll actually have a laser diode. Now, the laser diode doesn't deal with electricity, it deals with light. So different pulses of light will determine if the bit is a 1 or if the bit is a 0. Now, something that I find super interesting is on this next slide, we actually have just a brief little example of how a microphone works. So when you think about it, you can go ahead and play that video. When you think about it, you see in the video the sound waves hitting the top of the microphone. That top of the microphone is like a diaphragm that's going to move the coil inside of the microphone. And then based on the frequency of the sound, that determines how much the spring moves. How much the spring moves determines the frequency that gets transmitted through the actual wire, which is directly translated to the bits or the 1s and the 0s that can then be transmitted to an amplifier, then transmitted to a speaker, and then actually heard over a loudspeaker, which I find incredibly interesting. And obviously there are many other ways, like how massive images can get transmitted across wires. All of these things, when you break it all down, it all comes down to the bits, the 1s and the 0s, either the electrical charge or the light that goes through the actual physical wires and gets to the other computer. Now, to give us a little bit of a wrap up and some of the current problems and things that we're facing, I'll pass it over to Cole.
Thanks, Will. So as we all know, the internet is something that is very important to the whole world because the whole world needs data, and that's transmitted through the previous ways we've talked to. For instance, in class, we talked about underwater sea cables. These are fiber optic cables that use light or photons to transmit bits in order to allow data to pass through. They work fast and they allow traffic to connect all over the world. However, there are some downfalls and some barriers that we're seeing in the physical layer currently. One of those things that these things have physical damage happening to them all the time because they're in the sea. Boats are accidentally cutting them up, or just things are happening to them that's causing them to be damaged. Another thing is people could technically tap into them and hack, and so that's a big problem with this type of physical layer that we're seeing right now of underwater sea cables. Another thing is satellites. Now, satellites, the cool thing about them is unlike underwater cables, they are physical, but there's not as many things around them that will affect them from getting broken or damaged. And so satellites are very cool that way. However, there are some problems with them as well. Although they are available to everyone anywhere and you can get internet anywhere, they're slow, they're expensive, they have data caps, and most of all, you cannot use VPN with them, you can't encrypt with them. So what we believe the future is of the physical layer transferring bits across the world is through something called optic wireless. Now, optic wireless is kind of like fiber optics. Could you go to the next slide there? It's like optic wireless is like fiber optics. It's extremely fast. It's using light to transmit. However, it's using, instead of radio waves like a satellite would use, it's using light. And the nice thing about this is that it's immune to interference. So a big problem with radio waves or even cables using photons is that there's interference happening, you're losing data. So this is really cool. It's something that's not really being used yet. It's in a lot of academic papers, but the cool thing about it too is it can transfer 10 gigabytes per second, so it's really fast. However, there are problems with it. Weather can affect transmission, and you must be in a direct line of sight, or else huge data loss occurs. So that's kind of where we are at now, and where we're hoping to become, hoping to go in the future with the physical layer. And just to wrap it up here, it's a miracle how networks work. It's a miracle that we were able to transfer stuff from one side of the world to the other in less than a second. And it's something that is a blessing and allows us to be in communication with all over the world and get a lot of things done. So this is our presentation. Thank you.